The first time cells learn to die. For billions of years, life existed as single cells. For a bacterium, suicide makes a little evolutionary sense. Its goal is survival and reproduction. But everything changed when molecular organism appeared. Now individual cells become members of a large society. The survival of the organism become more important than survival of a single cell. A rebellious cell could threaten the entire body. Therefore, evolution developed a remarkable rule. If a cell becomes dangerous, it must eliminate itself. Apoptosis was born. This innovation helped create complex organisms, including humans. Without programmed cell death, advanced life forms probably could not exist. So what actually triggers apoptosis? A cell doesn't wake up one day and randomly decide to die. Specific signals activate the process. Scientists generally divide these signals into two categories. External signals, messages coming from outside the cell. Examples include immune system command, DES ligands such as FAS ligand, TNF-alpha signaling, neighboring cells requesting removal. Internal signals, messages originating from inside the cell. Examples include DNA damage, radiation exposure, oxidative stress, mitochondrial dysfunction, protein misfolding, severe infection, loss of survival signals. When enough danger accumulates, the cell enters a critical decision-making phase: repair or die. In apoptosis, one of the most important is p53. Scientists often call p53 the guardian of the genome. Its job is simple: constantly monitor DNA integrity. Whenever DNA damage occurs, p53 appears. First, it attempts to repair. It essentially tells the cell, fix the problem. If repair succeeds, the cell survives. If damage becomes too severe, p53 changed its message. Now it says, this cell is too dangerous to keep alive. At that point, apoptosis begins. This mechanism prevents mutated cells from becoming cancerous. In fact, mutation in the TP53 gene are among the most common genetic abnormalities found in human cancer. The mitochondria make the final decision. This is where the story becomes dramatic. Inside almost every cell are mitochondria. Most people know them as the cell's power plants. But mitochondria are also executioners. They contain proteins capable of triggering death. Normally, these proteins remain locked away. The key regulator are two opposing teams: the protectors and the executioners. These proteins promote apoptosis. Life inside the cell is a constant tug-of-war between these two groups. When damage overwhelms survival mechanisms, BAX and BAK punch holes in the mitochondrial membranes. Suddenly, a protein called cytochrome C spaces into the cytoplasm. This is the point of no return. The death sentence has been signed. Building the apoptosis. Once cytochrome C enters the cytoplasm, it meets the protein called APAF1. Together, they assemble a massive molecular machine, the apoptosis. Think of it as a biological execution chamber. The apoptosis activates caspase 9. Caspase 9 then activates executioner caspase. These enzymes begin dismantling the cell from the inside. The execution phase has begun. Caspases are specialized proteins designed for one purpose: controlled destructions. They cut hundreds of cellular protein with astonishing precision. Unlike necrosis, which is chaotic and inflammatory, apoptosis is organized. The cell carefully dismantles itself. DNA gets fragmented. The nucleus shrinks. The skeleton collapses. Organelles are packaged. Everything happens according to a strict biological program. So what does a dying cell look like? As apoptosis progresses, remarkable changes occur. The cell shrinks. Its membranes begin to form bubbles. Scientists call this blebs. The nucleus condenses. DNA fragments into small pieces. Finally, the cells break apart into membranes-bound packages. These are called apoptotic bodies. Importantly, the membranes remains intact. The cell's contents do not spill into surrounding tissue. No inflammation, no alarm, just a silent disappearance. A dead cell left behind could become dangerous. Therefore, the body has cleanup team, macrophages, professional cellular recyclers. Apoptotic cells display special signals. One famous example is phosphodiesterone exposure. These act like a molecular flag saying, "Please remove me." Macrophages quickly engulf the dying cell. The components are recycled. Within an hour, almost no trace remains. Apoptosis creates your fingers before birth. One of the most beautiful examples occur before birth. Early human embryos develop paddle-like hands. The fingers are initially connected. Why don't we keep webbed hands? Because apoptosis removes the tissue between developing fingers. Millions of cells die at precisely the right place and time. Without apoptosis, normal limb formation would not occur. This literally helps shape life. And what happens when apoptosis fails? Now imagine cells stop dying. The consequences can be catastrophic. Damaged cells accumulate, mutation build up, cancer risk raises, immune cells that should be removed survive, autoimmune disease emerge, developmental abnormalities appear. Many cancers survive because they learn how to disable apoptosis. The cell becomes biologically immortal, a dangerous form of immortality. Cancer is the great escape form of death. Cancer cells are masters of survival. Many achieve this by blocking apoptosis. They may mutate p53, overproduce BCL2, disable Caspases, ignore death signals. As a result, cells that should die continue dividing. Modern cancer therapies often attempt to reactivate apoptosis. Many chemotherapy drugs work by causing enough DNA damage to trigger the suicide program. New targeted therapies attack apoptosis pathway. Too much apoptosis is also dangerous. Surprisingly, excessive apoptosis can be just as harmful. Neurons lost in neurodegenerative disease often die through apoptosis-related mechanisms. Examples include Alzheimer's disease, Parkinson's disease, Huntington's disease, heart attacks, strokes, and certain immune disorders. In these conditions, too many cells activate death programs. So balance is everything. Apoptosis and aging. What role does apoptosis play in aging? This answer is complicated. As we age, DNA damage accumulates, oxidative stress increases, mitochondria become less efficient, more cells are pushed toward apoptosis. Meanwhile, some damaged cells refuse to die and enter senescence. These zombie cells remain alive but dysfunctional. The balance between apoptosis and senescence appear to be a major factor in biological aging. Researchers are actively studying whether manipulating this pathway could slow age-related decline. Lifestyle factors that influence apoptosis. Although apoptosis is genetically programmed, lifestyle affects it. Factors associated with healthier cellular regulation include regular physical activity, balanced nutrition, reduced chronic inflammation, avoiding tobacco exposure, maintaining metabolic health. Chronic oxidative stress, obesity, persistent inflammation, environmental toxins, and radiation exposure can all alter apoptotic signaling pathway. The goal is not to maximize apoptosis, the goal is to prepare regulation. Cells should die when necessary and survive when appropriate. Right now, as you are watching this video, millions of cells inside your body are making an extraordinary sacrifice. Some are repairing themselves, some are fighting infections, and some are quietly preparing to disappear forever. Life survives not only because cells can live, but because they know when to die. Every finger on your hand, every healthy tissue in your body, every defense against cancer, every stage of development depends on this invisible act of cellular self-sacrifice. In the end, apoptosis is not really a story about death. It's a story about how life protects itself. And that may be one of the most remarkable discoveries modern biology has ever made.